So this talk should be about 25 minutes, and then I hope that you would like to stay a bit longer for discussion and questions afterwards. Let's get started. So nice to meet you. My name is Tobias Stål. I'm a research fellow at University of Tasmania in Australia, and I'm also working at the Australian Centre of Excellence in Antarctic Science and the Compute Antarctic group here at University of Tasmania. I'm a co-chair of the SCAR Instant Committee for subglacial or for geothermal heat. And Instant is a SCAR initiative to better understand thresholds and instabilities in the Antarctic ice sheet. Apart from geothermal heat, I'm also interested in seismology in the broadest sense, and information theory and polar exploration and science history. So welcome to Antarctica. Antarctica is very big, very flat in some regards, very white, but it's also the continent of extremes. The highest elevation, the coldest, the most remote, the least known continent. And for a long time, our observations from Antarctica has been quite optimistic at the best. But in the recent years, particularly since the last International Polar Year, we have started to collect data more systematically and starting to understand Antarctica better and all the complexity. It's big. Here's a map of Europe and Antarctica overlaid. We could have done the same map with Australia or American lower 48 states or India or any part of the world, and we'll find that Antarctica is indeed a fairly big landmass. And the geology in Antarctica is just as diverse and complex as any other continent. There is a few reasons why we, I shouldn't say all of a sudden, but why we're now so interested in Antarctic geothermal heat. There is a big urgency to understand the Antarctic ice sheets and how they will respond to the global ocean warming. We just don't really know much about Antarctic geology, to be honest. I will touch a bit more on that later. So because of that, we can't really predict what kind of tipping points the ice sheets might run into in future. Working with Antarctic-related problems is also very rewarding. So I'm saying that to all geothermal heat flow people out there, because we have a great community collaboration. The Antarctic Treaty System sort of have been fostering a culture of global collaborations and data sharing. And when it comes to geothermal heat, there is a lot of method development that's happening right now in Antarctica when it comes to modeling geothermal properties or analyzing the geothermal properties. What we really need now is to connect the Antarctic geothermal community with the global geothermal community, and also to create stronger links with the glaciologists and ice sheet modelers, and try to understand how solid Earth and ice sheets are interacting. I will discuss that more further on. This is a geological map of Antarctica without any legend, but it gives you the idea about how poorly understood the continent is. Only 0.17% of the continent is exposed. The rest is covered under ice and snow. We know as a general concept that West Antarctica is younger, Phanerozoic mainly, still active tectonic with volcanoes and active rifting, whilst East Antarctica is generally much older, Archean and Precambrian, and it contains very big cratons. The exact extent is again poorly understood, but big cratons and cross-cutting Proterozoic origins. And to approach Antarctic geology, we can either use a kind of a deterministic approach, where we are mapping out a tectonic reconstruction and extrapolate properties and the history onto the Antarctic continent, as done here in the figure to the left. Or we can use some kind of probabilistic approach, where we try to sort of map out the uncertainties and understand like what can we learn from the data sets we do have. So this map on the right shows mapped changes in potential field data sets of Antarctica and where they agree of mapping a deep-seated crusted boundary or lithospheric boundary. When it comes to geothermal heat, we have similarly poor data in Antarctica still. This diagram shows on the leftmost column the area of the world represented by different tectonic plates on the upper part of the figure, and the lower part of the figure shows different types of lithology on the terrestrial part of the globe. And the bar to the right of that shows the distribution within the international heat flow compilation that we are all very engaged in developing. This figure is a few years old, so these have maybe changed a bit in the last compilation. But the takeaway message here is that when it comes to measurements from Antarctica make up 11.5% of global surface, but only 0.7% in the heat flow population. And of those 0.7%, most of those measurements are from the shelf. And when we look at different shallow lithological types, ice and glaciers make up 27.8% of the terrestrial surface of the Earth. But if you round it up to the next tenth of a percent, there's almost no measurements in ice and glaciers in the compilation. It's actually so few. So if we were to weigh the measurements in ice and glaciers, we have to weigh each measurement 814 times just to make it compatible with other types of surface geology. I borrowed this cartoon from this brilliant webpage on Antarctic glaciers, which have a lot of fantastic outreach material for anyone interested in glaciology in general or Antarctic glaciology in particular, showing that to some extent Antarctica is not very different from other continents. We have water evaporating from the surrounding oceans, wind and weather patterns are moving that humidity over the continent, and then it falls as snow. A little bit is returning to the atmosphere by sublimation, but most of the snow over the Antarctic continent is falling as snow and is then redistributed by wind. And it's also important to remember that the interior of Antarctica is in all regards a cold desert. So the precipitation is usually very low. However, it is increasing in many parts of Antarctica due to the atmospheric warming at the moment. Once snow is accumulating, it's accumulating year by year, eventually forming granular ice and firn, which is as close to ice as you can get. And eventually the pores are closing and you get glacial ice. And the ice is then, due to its own mass, flowing towards the coast. Getting closer to the coast, it's speeding up, forming fast-flowing outlet glaciers that eventually meets the ocean and then calve off icebergs or melt at its base. And the speed at which the ice is moving varies a lot. So here we have two maps of Antarctica and Greenland. I attempted to put Greenland on the right scale in relation to Antarctica. And please note that the color scale is logarithmic. So for most of the interior of Antarctica, the ice is moving very, very slowly. But once you get closer to the coast and those outlet glaciers I'm talking about, then the ice is speeding up at the surface and can reach velocities of well over 1 kilometer a year. So what has all this to do with geothermal heat? Particularly as the solar irradiance is about 2,000 times more than the geothermal heat that reached the ice sheets from the base. Well, it turns out that it also matters where we got the heat, because the ice sheets are a fantastic isolation. So geothermal heat at the base of the ice sheets can cause basal melting, forming subglacial lakes, and water saturating the sediments on the glacier. And it also changed the mechanic properties of the ice itself, as I will get back to a bit later. I like to think about it in the context of those humble tea kettles. You know, one of those tea kettles. It's usually one in every tea room at every university. Each of them are about 1,000 watts. And the geothermal heat on a global scale is usually represented by one of those, can be represented by one of those kettles about every 100 meters or 180 meters apart, deep in the crust, so continuously generating heat over the centuries. And if we bring this kettle analogy to subglacial context in Antarctica, we can make a bit of a napkin calculation and calculate how much melt each tea kettle or each area represented by about 30 by 30 meters will generate since the last glacial maximum, which is about 20,000 years ago. And each of those tea kettles produces about 2,400 cubic kilometers of water for a long time. And this is a big implication for the thickness of the ice, the stability of the ice, and the distribution of the ice. Here's an experiment I made a few years ago where I put a bit of white chocolate on a hot plate. And as I'm heating up the hot plate, the chocolate, here representing, of course, the ice sheet, is changing its friction to its base and is accelerating as a response to the warming. It's a bit of a side note. Initially, this experiment was not very successful. It turns out that when I started to melt the chocolate, it actually stuck to the plate rather than sliding on it. So for a brief moment, I was questioning everything we worked on for the past decade, but it turns out with the right heating and the right chocolate, it worked fairly well. And this is sort of the picture I was wanted to bring along when we look at the ice sheets. So geothermal heat causes spatial melting. We can model that melting on continental scale. How much ice or how much of the total accumulation in Antarctica have to leave the continent as melted water at the base of the ice sheet, or typically at the base of the fast-flowing glaciers, outlet glaciers. And we can do similar modeling work on the local scale. And when we do it on local scale, we can also take advantage of detailed radar data or other detailed observations. When we are mapping the base of the ice sheets, we are typically within this little black polygon here. And we, at the base of the thicker ice sheets in Antarctica, which can be 3,000 to 4,000 meters thick, we get to a point where actually the melting point, pressure melting point, is a few degrees below zero. That further accelerates the melting of ice. It also complicates how the ice is channeled away from the base of the ice sheet. We have a lot of refreezing, for example, when water is flowing from higher pressure to lower pressure, and it refreezes to the base of the ice sheet. So now try to talk a bit more about geothermal heat. This is a map a few years ago, but as far as I know, it didn't change since. Well, it changed. It's one more measurement since this map was generated. But in the picture is the same. There are very, very few measurements of geothermal heat in the Antarctic continent. And those measurements we have are quite often, well, partly they are at locations where we already have existing infrastructure. So they're not really placed based on a particular scientific question, but rather where can we actually have the infrastructure to drill through the kilometers thick of ice. And they're also often targeted on understanding the age of the ice. So we've been drilling with a particular interest of finding the oldest ice, which is at the interior where the ice is flowing very slowly, and also where the geothermal heat flow is very, very low, so that you get little basal melting, so you can preserve the oldest ice. There are a few exceptions from that, of course. There is, for example, the Vostok drilling that was targeting the Lake Vostok beneath the ice sheet. To the left here, we see the temperature gradients for some of those drillings through the ice sheet. And the first thing you might notice is that some of them are much steeper than others. And the steepness of the temperature gradients within the ice sheet is a result of the accumulation of the surface. We have a lot of accumulation. You preserve the surface temperature deeper down, and also the amount of basal melting. If you keep on melting off the base of the ice sheet, then you create a steeper gradient at a deeper part of the ice sheet. The figure to the right shows in a bit more detail a few selected measurements, and also includes one from a coastal site, the Lower Dome, where we have a very high accumulation because it's much more precipitation along the coast. And here you can see how the temperature from the surface is preserved deeper into the ice sheet. And we might even see a bit of a kink at the surface representing recent surface temperature changes. We can use the same kind of thinking and knowing a bit of the history of the ice sheet from radar measurements. We can also reconstruct the temperature gradients back in time, which is of great importance for ice sheet models that want to run over longer time periods. So we have an example from the West Antarctic ice sheet from the ice divide, where we can see how the temperature gradient likely has changed, model result, how the temperature has changed since the last glacier maximum and further back in time. And common for all of them is, of course, that at the surface, we see temperatures that represents today's climate. So it can be down to -50 or thereabout at the Vostok or those high elevation sites in the interior. But down at the base, we reach the pressure melting point around 0 degrees or just under 0 degrees. It's not only basal melting that is caused by geothermal heat, but we also change the mechanical properties of the ice itself. And temperate ice have different elastic properties or mechanical elastic properties than colder ice. This diagram to the right shows in relation to the melting point, if you have even at 10 or 15 degrees colder than the pressure melting point, the ice can be much more reformed, can change much more rapidly with a different I'm supposed to say. The ice has a different ability to deform. And this figure also shows very cunningly, once you get to the pressure melting point and you start to form water within the ice, even a few percent of water can rapidly change the ability to deform of the ice. And the figure to the left also shows the velocities at different depths. So where the ice is warmer, that's where most of the deformation of the ice is happening. Looking spatially, it doesn't take much to really impact a vast area of the ice sheet. So this is like an experiment that is based on an ice sheet model with real observations, and then the authors introduced synthetically a small area with elevated geothermal heat in some selected sites in the interior of Antarctica near the Prytz Bay and the Emery Ice Shelf. And just by introducing a very small area with elevated heat, they changed the stability of the ice sheet over vast distances around it. So by introducing high heat, not only did they accelerate the ice sheet locally where this heat was elevated, but they actually also slowed down the ice in other areas. So there's a complex interaction between geothermal heat and the ice sheet velocity or stability. Not only is the question regarding the distribution of the geothermal heat, but also, as it turns out, a question about the resolution of the geothermal heat when the geothermal heat values that we enter into an ice sheet model. So this is again a synthetic experiment where the authors took the average geothermal heat from different models. I will talk a bit more about that later. And then they redistributed that heat into a kind of a Gaussian noise field, and then they applied different filters to change the wavelength of the variations in geothermal heat. And they were careful to preserve the total geothermal heat for the catchment basin at every experiment. And what I could see is that there's a kind of sweet spot where the ice sheet seems to be most sensitive for variations in geothermal heat. And that is unfortunately at a higher resolution than the heat flow models that we can produce on the continent today. So for this audience, of course, I don't have to explain where geothermal heat is originating from and how it's formed and how it's refracting up through the crust. But it's just a reminder that the geology, the subglacial geology in Antarctica is just as complex as anywhere else in the world. And we should really expect to see the same variability as we see in Australia or Africa or North America or anywhere else. A lot of the heat is, as you know, generated through heat production within the crust, and depends on what rocks you have. The total heat production can vary over a large range. Those green dotted lines on the right figures show some kind of ideal case where, depending on your crustal thickness and your heat production, you can vary the heat flow over a large range. And we simply don't know the crustal components in Antarctica well enough to map out the heat production on a big continental scale. There are some very promising recent studies that have been attempted to doing it by using different potential field data and petrophysics. But we are still a long way to actually reach a point where we can model crustal heat production at the resolution and accuracy as required by ice sheet models. Looking at other data sets that are more or less associated with geothermal heat in other continents and in other studies, we see that there is all those subfigures here that they show geothermal heat in the International Heat Flow compilation on the y-axis, and then different observables on the x-axis. And there are some, of course, we see some association with the lithospheric thickness, which you can derive from seismic data. And we see some association with the distance to volcanoes or seismic wave speeds in the upper mantle and so on. But it's really hard to pick one observable that is correlating strongly enough with geothermal heat to provide us with a strong estimate of geothermal heat in the subglacial regions of Antarctica. The upper right corner here, for example, shows the Curie temperature depth from a global model using a spectral analysis of the magnetic field, and we don't really see any association with geothermal heat from that. So there's been a lot of attempts. So these are all six out of maybe 10 or 12 or more attempts on modeling the geothermal heat of Antarctica. The upper 4 models are all empirical. So they've been using different observables, one or many, to compare Antarctica to other continents where we have heat flow measurements that we can then project to the Antarctic continent. And the lower 2 maps shows forward models where the authors have been using magnetic data to estimate the Curie temperature depth and then calculated the resulting heat flow from that. And as we see, there's not much of an agreement, and this has caused a lot of frustration in the ice sheet modeling community that want to use a geothermal heat flow model as an input for their ice sheet models, but have not been able to use so in a robust way because it's been such a big disagreement and debate about what is the geothermal heat that I should be using. So really to divide into ways, two streams of thinking. Some people have been working on forward models and some people have been working with empirical models. And thankfully, we're now at the point, I believe, where the data is good and detailed enough, and the methodology has been developing over the past decades. So we start to get a more holistic idea about geothermal heat in Antarctica, and we are learning from each of the models that are generated. And we also see that models are starting to converging. So these are two recent studies. The model to the left is based on forward modeling. The authors use different observations of the density and the seismic properties to calculate geochemistry and thermal gradients in the lithosphere, and they forward calculated this geothermal heat flow model. And the model to the right is a sort of a brute force statistical model that used any observables we had for Antarctica and compared it to the global heat flow compilation, and then populated the continent with those calculated values. And we start to get close to a very good agreement between those different kinds of models, even though they're not using the same data sets and very different methodology. Here's some more examples of recent geothermal heat flow models of the Antarctic continent that's starting to converge. And more than that the models are converging, we also really learn by comparing them. We can see how different observables are impacting the interpretation of the geothermal heat flow field. And we can also see how different methods are controlling the resolution and accuracy of the models. So unfortunately, as you saw on a slide earlier, that the heat flow, the ice sheet modeling community, they really need higher resolution in their heat flow models. And we know, again, I don't need to preach for this audience, but we know that the topography has a large impact on how heat is transferred from Earth's interior up to the surface. And this is a brave attempt to start to mapping out the topographic refraction factors. So the left column is a unitless ratio of heat concentration, if you like. And then if you overlay that on a continental scale model, as in the center column, we get much refined geothermal heat flow map as on the right column. Unfortunately, this is really something we have to do, and we need to test it and develop those methodologies, but it's a very tricky thing to do because the thermal conductivity of different rocks varies over a large range. And again, we don't really know what geology we have under the Antarctic ice sheet. So depending on what kind of sedimentary rocks we have in the uppermost few hundred or up to a kilometer in the big sedimentary basins, the resulting geothermal heat could either be concentrated into the depressions or concentrated into the ridges. So there are a few attempts to start using the Bayesian topography to refine continental scale heat flow maps, but again, it's associated with very large uncertainties, and it's been quite a while until we get a good handle on how to do it right. So the figure on the right here shows the conductivity in ice at different depth or different pressure, if you like, and different temperatures. But depending on the temperature of the ice and depending on the geology, the relation between the thermal conductivity of the ice and the shallow geology can be completely reversed. So where we're standing right now, apart from trying to improve our models and iterating them and considering new observables, we have also entered like a stage where we are engaged in much more discussions with glaciologists and with the ice sheet modeling community to really understand where geothermal heat flow matters, what is the accuracy, what is the certainty that they will need to produce robust projections of the future sea level changes, and what kind of format of uncertainty metrics, for example, is useful for their modeling work. This concludes my presentation. I'm very happy for questions or comments, and more than anything, I'd also like to invite all of you here to engage in Antarctic geothermal heat flow, particularly those of you who are working on continents that in Gondwana was connected to Antarctica. I'm sure you have a lot of good observations and insights that we should consider when we're working in an Antarctic setting. So thanks a lot.